Oxygen consumption, such an important concept that we need to understand when we talk about running, swimming, and or biking. VO2 represents how active the aerobic system is to convert chemical energy to mechanical energy, in essence. So in this class, I'll present to you VO2s from several different perspectives. And each perspective gives insight into endurance performance a little differently. And we're going to have to really pay attention to some of the details of each way that I'll be presenting and others will be presenting VO2. So what I have here is a spreadsheet that I just generated some data from using the American College of Sports Medicine equation for VO2. This is a standard equation, and I encourage you to be familiar with it. I will not test you on the equation. I will not ask you to solve for anything using the equation, but you should understand the equation and what it's used for. When I work with students on research projects where we measure VO2 during running, in this example, I'll ask them to estimate what the VO2 should be using ACSM's equation. And that's usually a good way to make sure our equipment is operating the way we're expecting it to operate, because we'll get a pretty good ballpark estimate of rate of oxygen consumption using the ACSM equation. So I've got that equation here. Again, I'm not going to test you on the equation. I'm not going to ask you to solve for VO2, but I want you to understand the source of these data and then ultimately how to interpret these plots. So what I have here is a data set that includes speed, and this is miles per hour, and then I converted it to meters per minute. You have to use the correct units in this equation to make it work. And then I've got different grades, 0%, 5%, and uphill, and then 5% downhill, so negative 5%. And then I just calculated VO2 using this equation to determine the rate of oxygen consumption. Whenever I use the word rate, that we know that the denominator of this VO2 value is a time denominator. And typical units are per minute. So we've got milliliters of oxygen per kilogram body mass per minute. So this is a rate of oxygen used. And this is just normalized to body mass. All right. So I could, so a rate of oxygen consumption. That rate of oxygen consumption is going to be influenced by lots of different things. I'm just illustrating one factor, which is grade. And this is how we would expect VO2 to, well, actually I'm showing two factors, speed and grade. So what do I have here? I've got this first plot right here. And whenever you look at data illustrated in a plot, I want you to really look at and pay attention to what is plotted on each axis. This is the horizontal axis, this is the vertical axis. Always look and see what is plotted here. In this case, this is speed, and I left it in miles per hour. And this is VO2 in units of mLs per kg per minute. All right, we're gonna change these units in just a bit. So this is VO2, look at the units, mLs per kg per minute. This is very common to see these units, or liters per minute would be another set of common units. The per minute tells us this is a rate of oxygen consumption. Technically, I should put a dot over the V because that tells me it's a rate, but it's a pain in the neck to put that dot in Excel. And so I've left that out. So this is just using the ACSM equation to predict VO2 from speed, knowing what elevation the person's running at. Blue is 0%, orange is uphill, 5%, and gray is downhill, negative 5%. So what do we have here? Well, this is very characteristic data that if we got on a treadmill, for example, and we left the treadmill level, and then we just started increasing the speed, okay, just like a graded exercise test. What we would expect VO2 to do is increase in a linear manner. Linear meaning a straight line, all right, and that's that blue line. So for every increase in speed, I get an equal increase in VO2, rate of oxygen consumption. A couple things to notice here. VO2 is increasing at a linear rate. The other thing to notice is the rate of increase of VO2 is dependent on which elevation I'm running up. If I'm running uphill, that VO2 is going to increase at a steeper slope. If I'm running downhill, VO2 is still going to increase, but at a lesser slope. Now I have an illustrated of VO2 max here. All right, VO2 max is the maximum rate of oxygen consumed. And that's just the end point. That's the VO2 at the end point of our graded exercise test. I'm just making this line go out. So this is just, using an equation. 10 miles per hour is about a 6-minute mile. 15 miles per hour is fast, okay? So this is a really fast speed. This is 10 miles per hour is a very good sustainable pace for 5K, about 19-minute 5K. And then this is obviously slower. Now I've left some slow velocities in here, 1 mile per hour, 2 mile per hour. This equation is for running specifically. There's another equation for walking. Now there are times where in these speeds, we may actually want to walk versus run. In that case, these data points are not accurate. So if I'm using walking, I have to use a different equation. Right now, I'm just using running. And I'm just illustrating the data we would expect if we ran at 1 mile per hour, 2 miles per hour, 3 miles per hour, 4 miles per hour, what have you. We typically want to start running around 3, maybe even closer to 4 miles per hour. Down at 1, 2, and 3, we tend to want to walk. So there's something else going on down here. But nevertheless, using this equation, if I just put speed in and I put grade in, I will get an increase in VO2 as speed increases, and the rate of increase of VO2 is going to be dependent on the elevation I'm running at. That's just using ACSM's equation. All right, let's look at another way that we'll look at VO2. And that's VO2, rate of oxygen consumption, mLs per kg per minute. I know it's a rate because it's the per minute here. The mLs is the amount of oxygen. The kg is the body mass. On my y-axis is rate of oxygen consumption, mLs per kg per minute. On my x-axis is time. So not speed, but now time, all right? And we've got to watch this. We've got to watch what's being plotted on each axis. And what do I have here? I've got the 3 lines again, running at, in this case, I put in 10 miles per hour, at 5% grade, at 0% grade, and downhill 5%. So the rate of oxygen consumption for running at a constant speed is going to be greater when we're running uphill. So trying to run a 6-minute mile up a 5% grade requires a greater rate of oxygen consumption than running at a level or running downhill. Okay, so this is another way to look at the data. So this would be analogous to running economy, the rate of oxygen consumption for a given speed. In this case, that speed is right here in my equation, 10 miles per hour. This is the rate of oxygen consumption for running that speed at 5%, 0, and minus 5%. Okay, so that's the second way that we'll be looking at VO2. The third way is a little tricky, and we'll spend some time on this, and you'll see some other presentations on this. But we're going to use a new term called energetic cost of locomotion. So really here, I should have put in here, this is running economy. Okay, VO2 rate of oxygen consumption, because it's got a per minute here. This is VO2, energetic cost of locomotion. When I use this term, energetic cost of locomotion, what I mean is the amount of oxygen consumed per distance. All right, so now I've got a new set of units, and you see this, I've highlighted that M. The way that I've done this, I've just used that as meters. Typically, an energetic cost of locomotion would be per kilometer. So how much oxygen do we consume to run, in this case, a meter, or 1,000 meters, a kilometer, all right? That would be, the way we would do that experiment is you would be hooked up to a snorkel, if you will, mouthpiece, and you would be exhaling air into a bag, into like a balloon. And as you run your kilometer, 1,000 meters, that exhaled air would collect in that balloon. And then we could determine the volume of oxygen used to cover that 1,000 meters or a kilometer. That ends up being a new term called energetic cost of locomotion. For those of you who are math-minded, the slope of the rate of oxygen consumption versus speed plot is energetic cost of locomotion. I'll go through that in another presentation in more detail. So all this is telling us mathematically is the slope of these three lines. Energetic cost of locomotion is the slope of the rate of oxygen consumption versus speed plot. So I've got speed down here. I've highlighted that in red because it's not time anymore. And I've got volume of oxygen consumed per distance. In this case, that distance is meter. All right, so what are we looking at here? Now I've got this much oxygen consumed regardless of what speed we're running at. All right, let me say that again. This is the amount of oxygen consumed for any of these speeds. So if I ran at 2 miles per hour, I exhaled, I used, I said that wrong. I used 0.25 milliliters of oxygen per kilogram body mass for every meter, okay? And it doesn't matter what speed I ran at, I consumed the same amount of volume of oxygen. Now, that looks like, this plot looks like this one, but the x-axis here is time. This is speed. Totally different concept, okay? Totally different concept, even though the plots look alike. This is running at 10 miles per hour at 5% grade. I would expect to consume 70 mLs per kg every minute, okay? Every minute. So that's my rate of oxygen consumed. So if I ran 60 minutes, I would be consuming at every minute roughly 70 mLs per kg per minute. This is telling me if I'm running at, here's 10 miles per hour here. If I'm running at 10 miles per hour at 5% grade, this is telling me the volume of oxygen consumed, which is a 0.25 milliliters per kilogram for every meter. Totally different concept. And this is going to be important for us to understand the advantage of this. But look at this, the volume of oxygen consumed is constant for all these speeds, constant at running level and constant at running downhill. What we'll discover as we go through this class is the volume of oxygen consumed per distance equates to calories used. All right, so what does that tell us? Well, it tells us that the amount of calories used to cover a particular distance, for example, 1 kilometer, is the same if I run at 3 miles per hour or 9 miles per hour. The amount of calories is the same. The rate of calories used will be quite different for the different speeds. This is telling us this would be analogous to rate of calories used. As I run 10 miles per hour, the rate of calories used is higher than if I run 4 miles per hour. Okay, the rate of calories used. I'm using calories faster. But if I look at the amount of calories used per distance, the math tells us it should be the same regardless. So if I run a mile, I'll use about 100 calories, regardless if I run that mile in a 10-minute mile or a 6-minute mile. So if I run it really fast, let's say 5-minute mile, okay, that's going to take me 5 minutes to get that mile done. And I will have consumed 100 calories, or excuse me, I would have used 100 calories. But I've run at 10 minutes per mile, that's going to take me twice as long to do that mile. It's going to take me 10 minutes, but I still would have used only 10 or 100 calories. But the rate of calories used is quite different between those two examples. Okay, so the amount of calories used is often what we want to know when we're trying to figure out a nutrition plan for an endurance event. We want to know how many calories it's going to take to complete a marathon, a 10K, a 21K, whatever it is. Or if we could translate this to biking or even swimming. All right, so energetic cost of locomotion is a different concept, although mathematically directly related to rate of oxygen consumption. We'll do this some more as we go through the semester. What I want you to really pay attention to is as you look at data from VO2, look at what's on the y-axis, what units are being used, and what's on the x-axis, whether that's speed or time, and then on the y-axis, whether it's rate of oxygen consumed or amount of oxygen consumed per distance. Rate, you'll see the time in the denominator. For energetic cost of locomotion, volume of oxygen, you'll see a distance in the denominator, meters, kilometers, miles, if you even want to go on that route. Okay, so those are the different ways that we'll be looking at VO2 in this chapter, chapter 2, and then as we continue on the semester. All right, thank you.